Okay. Whoops. We're kind of getting all the graphing questions out of the way. Graphing and that, I guess we're just looking at why, like why are we graphing things, and what does it even mean for a graph to exist? Like you think of a parabola and it's like, yeah, cool, it's a parabola, but like, what does it mean? Like, why does it go down really fast, and then why does it plateau, and then why does it go up? Like, why do we care about that? So we're going to bring a little bit of a real life context into the graphs before we start actually graphing, because we're going to start graphing parabolas like next week, or this week actually. So it's good to, I guess, understand what a graph means, what each of the segments of a graph mean, and I guess why do we even graph in the first place? Mic check. Sweet. Okay. This is going to be a 2-in-1, so I'm going to do 2 exercises in one, but they relate heaps, and I don't think they should be 2 exercises in the first place. I'm not going to give you 2 exercises worth of questions, but yeah. Okay, let's have a look at this. So I guess this is a real graph. It's a distance time graph, so time, distance. It shows the journey of a cyclist. What was the total distance they covered? So when it asks about things regarding the axes, then try and forget about this. It's not asking for the length of the line or anything like that. It's just saying how far did they go. And I guess if you just think about this for a second, he's starting here, he's going, yeah, okay, this line represents his journey, but it actually represents his speed. The distance is on this side. So how far does he get to? Well, he actually gets to 50 kilometers. Then he stops, and then he goes down back home. So this is kind of like where he's starting. The further up the graph he goes, that's how far away he is. The further across, that's how long he's been traveling for. So the distance in this case goes up to 50, and then it goes back down to 50. So his total journey is 50 kilometers away, 50 kilometers to, so that means it's 50 kilometers times 2, so that's just 100 k's. Just 100 k's. So he's traveled 100 kilometers. That's a pretty big ride. Okay, now we get into the interesting questions, and it's that the cyclist's speed increased at B. So they've told us that after the first hour. How is this shown by the graph? So like I said, when it goes up and down, that's the distance. When it goes left and right, that's the time. Now this line, so the actual line, represents how fast they're going. And I guess you can think of it in a couple of ways. The first way might just be like, oh, well, the lower the line, the less amount of time, sorry, the more amount of time it's taking to get a further distance, which just means they're going slow. So like in this case, the line isn't very steep, so they're not going very fast, but then it picks up the steepness, and now they're going faster. And I say the word steepness, but there's another word we can use, and it's gradient. If you think about the gradient of the line, that is the speed. So the gradient of the line is here, is low. So just remember this, from when we used to graph lines. When it was exactly 45 degrees, so see how I'm cutting the boxes perfectly, that was a gradient of 1. Anything lower than that was less than 1, so like a half and a quarter and stuff. Anything greater than that was like 2, 3, 4. So you can think of it like, if it's low, then they're going slow. If it's high, they're going faster. So they've said that at B he starts picking up the pace. Well, yeah, that's true because it's got a bigger gradient, or because the line's a little bit steeper. I keep talking to my phone, but I should be talking to the camera. Okay, so I'm not going to write that, but actually maybe I will. So what did they say? The cyclist, how is this shown by the graph? Steeper gradient. Okay. Calculate the speed. So now they want me to actually calculate the speed. Now, with no knowledge of lines or anything like that, you might deem this to be a little bit of a difficult task, but I'm going to show you how we, I guess, relate this to stuff we already know before. So the first one says from B to C. So we want the speed of this thing. I'm going to do this 2 different ways. I don't know if anyone remembers this. You might have done this in year 8, but let me just... There's a way to calculate distance, speed, and time. I don't know if you remember, but there's a little thing you can draw. It looks like this. This is called your distance, speed, time triangle. And I've written it down because I don't want to forget. So you kind of do this, and you're like, okay, what am I trying to find? Well, I'm trying to find my speed. So what I do is I put my thumb over. So I put my thumb over that. And then what have I got? I've got D over T. So that would be how I find my speed. So D over T, so speed equals d over t. Now from B to C, so from B to C, d is, so how far do they go? Well, they go 1, 2, 3, they go 4, what is this? What's this in tens? So 40 kilometers. So they go 40 kilometers. And how long does it take to go to 40 kilometers? Well, so from B to C, how long does it take? Well, that's what, 2 hours. So 2 hours. I don't know why I wrote a H there. So that means 20. Now this was in kilometers, and this was in hours. So this is actually where kilometers per hour come from. So distance was in, what did I just say? Kilometers. So kilometers. And time is in hours, so hours, hours. And let me just rewrite this as 40. Think of it literally as a fraction. 40 over 2 times km over h. Now, that's the same as times kilometers over hours. And look at this. Doesn't that look familiar? Like, that's actually how it's written. So the way that you've learned to write this is actually as a fraction. So you've been writing it as a fraction. It's just like per means fraction, like you're just a different way of writing it. Don't you think that's cool? I think that's so cool. Anyway, okay, that's the first way of working it out. The second way is, well, we actually kind of just did it without anyone really noticing. I was saying before that the speed is the gradient of this line. So why don't we just find the gradient of that line? Now the gradient's going to be, remember, you just make a triangle. Already found the rise. It was, what did I say, 40. This was 2 hours. Have a think about this. I just wrote this as a fraction. I wrote this as d over t. That's rise over run. D was the rise, t was the run. Look at the graph. D was the rise, that's the rise. That is that axis, and the run is time. So actually just finding the gradient of a line, and you didn't even really realize. Or maybe you might have. But yeah, I guess that's two different ways of looking at it. Maybe I'll just write that. So that's like rise. Whoops. That's run. Let's do that for the next one. So that was that I? Yeah, I. I don't know why I looked at that. I've got it on my screen. What color am I choosing? That's I. Let's do I the other way. I captain. D to E. So D to E. D to E. Now, have a think about this as well. It's going downhill. So what does that say about the speed? This is going to be a little bit confusing. Remember how I said like 5 seconds ago when this was the gradient? Well, kind of is, but you can't really have a negative speed because I'm going. This kind of suggests that I've got a negative gradient, which is true. Let's use a triangle. I can just hear the objections in the room at the moment. Bear with me. How many hours is that? That's 1, 2. That's 2.5 hours. Or mixed fractions. Don't like them. And then what was it? 50 kilometers. Okay, so the speed equals. Let's write it like this: rise over run, which is 50. Was it 50? Yeah, 50 over 2.5. Equal fractions and decimals. Well, let's do it like this. Remember, kilometers per hour. What's 50 divided by 2.5? Actually, know what that is. 20 apparently. 20 kilometers per hour. Okay. Let's call this method 1, method 2, yeah? Method 2. Method 1. Okay. What was I just saying? Oh yes, I believe there's going to be arguments as to why this shouldn't be negative, or should be negative. I'm going to try and convince you. Yes, it's negative, because the gradient's negative, but they're not slowing down, they're speeding up, because they're actually traveling somewhere. It's just... Oh, how am I going to explain it? It just so happens that like this graph kind of represents the displacement from here. So I guess maybe that's the science word to use. I'm looking at the displacement from here. In order to get away from this point, I need to have a speed. And I guess now here's my new origin. If now I want to move away from this point, then I need to have a speed. Can't think of another way to explain that. Oh well. Okay. There's still another one. D. D. when was the cyclist stationary? Okay, well, I can prove it to you using math, but it's pretty obvious when you just look at the graph. When are they stationary? Well, it's when they're not moving anywhere, or when their distance isn't changing. So the distance isn't changing between here and here. So that suggests that they're not moving away from their house. But I have a bit of a counter argument for you. Suppose this is their house. Suppose they traveled to here. This is A, B, and C. Suppose they traveled here. Now, if they just started traveling here, like this, and notice I'm drawing a circle, isn't this the same distance as this? So doesn't that mean that, yes, their distance from home isn't changing, but they are moving? I don't know, just thought that was an interesting idea to think about. But essentially, this graph, I guess, just shows that it's making the assumption that they're moving in a linear fashion, I guess. Like, here's home, here's my destination, it's going here and then here. Maybe, yeah, they pick up speed, so they go like here, and then they go fast, and they stop, and then they go fast, and then, but yeah, if you're asked a question like this, don't overthink it a little bit too much. Just be like, yeah, okay, they're not moving here. So between C and D. So from C to D. I don't know why I just thought it was interesting to think about the circle. Oh, it said, what do you notice? I didn't read that. What do I notice? I notice they're moving. I don't know. Okay. Does it say how long? No, it doesn't say. When was the cyclist? I guess between the third and the 3.5 hour. Okay, that's just the first one. This is going to be a long one, I think. Alright, so basically this is just saying that most journeys aren't just going to be a straight line, like they're not going to have what's called a constant speed. So constant means between here and here they were doing exactly 20 kilometers an hour, and between here and here they were also doing exactly 20 kilometers an hour. It's not really realistic. Like, you might pick up speed, you might not pick up speed. It's just saying describe each of these more realistic graphs, and a more realistic graph would be represented using a curve, which is kind of where we're leading towards. I'm not going to write this, but essentially you can just kind of draw you can draw little gradient markers on here if you wanted, kind of like that, and then start talking about them. But basically, this is they've got a slow speed, so in other words, they start at home, they're going slow, then they start to pick up the pace, and then they begin to slow down until they eventually come to a stop. That might be how you describe that one. This one, they're traveling towards home, so I guess you just call like this, the x-axis, or in this case the t-axis, you call that home, because this is kind of how far away they are from home. So here they're going home, maybe they're going downhill, they go really, really fast, then they slow down heaps, and you could argue that they stop here for a second, and then they start to pick up pace, and then they slow down as they approach home. This one, they start off slow, and then they increase their speed, and then because it's a straight line, they move at a constant speed for the rest of the journey. Well, there's no arrow, so I guess they just stop, but yeah, I guess that's how you could describe those three. Now, draw distance time graphs to represent each of the situations described. Now, it says draw, it doesn't say rigorously sketch, it just says draw it, or it doesn't say plot, so I'm just going to be very, very rough with this, but again, try and be a little bit neat. So, distance time graph, we'll call that t-axis, call that the d-axis. Now, this person was running quickly. It doesn't say what direction, so I guess we could just draw it kind of however we wanted. Let's just suppose that they started at home here. I'm actually going to draw this. They start at home. They run quickly. So I'm going to draw something with a really high gradient. They go quickly, but then their speed decreases until they stop. So their speed slowly decreasing. So see how so again, you can just draw little gradient markers on here. So see how my gradient is getting less and less and less until eventually they stop. So stop means they plateau and their line is straight. So that could be graph of the first one. I'm bigging that up a bit. Okay, so and then B. Hope that music's not too loud because it just felt like it got louder. T. I have a friend named Susanna. I was running home at a constant speed for 2 minutes. Running home, so that suggests that they're starting up here. Now for 2 minutes, so now it actually wants me to plot something. So let's put a 2 there. Now at a constant speed. Now it doesn't say that they get home, so I'm gonna pull up just short. So a constant speed means a straight line. So I'm gonna do a straight line to there for 2 minutes before slowing down and stopping 100 meters from home after a further minute. So a further minute, let's call that 3. That's when they're stopped. So they're stopped after that. But at this point they slow down. So slow down means like draw a little curve till they slow. So slowing down doesn't mean that I go like this and then I go bang. It means I go like this and then I do a little bit of a gradual line. So that's how I would describe that. Oh, and it's 100 meters. So that point there should be 100. So I'm going to draw that as 100. And I'm good. Maybe I need to put meters and minutes here. Okay. Oh, I don't like that line there. Or that line. Okay, so the next one's a lot easier. These are called informal graphs or graphs of change, and they're not really, they're realistic, but they're not like, they don't show an axis. Like it says noise level, but how is that calculated? What, decibels? It doesn't even say decibels here. So this is just a very informal type of graph. I just put the whole solution in here because I thought we could just talk about it. This talks about the noise level in our classroom. So I'm thinking our one would just be like this, but this is suggesting otherwise. It talks about the noise level and it's asking us how might this have happened. Well, you think about, here's 0, you haven't even entered the classroom yet, then people start walking in, it gets really loud, people are getting their stuff out, then maybe I start talking, so then it's quiet. So this is where it's a little bit quieter, so I'm trying to get everyone quiet, everyone's quiet, and then everyone starts picking up the noise again when we start working during the lesson. And then maybe I want to talk towards the end of the lesson, and then maybe you guys start picking up your noise when you start packing up, and then you exit the room. So that might be one way to describe the noise level. Now, this one's a little bit complicated. It appears like a trick question on the surface, but it's not. I was thinking when I first saw this, I was like, if water's poured in at a constant rate, then how much water is in it? Well, it's going to be constant, so it's just straight, but it's asking about the height of the water over time. So obviously the height's going to change depending on what part of the graph you're looking at, what part of the beaker or container or whatever. So if we just break it down, think about the first little part. So we'll call the first part A. This is kind of how the textbook's done it, but I couldn't expect you to be asked something like this, but you know. So we'll call like the different sections each thing. So between A and B, it's got the widest what am I trying to say? The widest capacity, volume. So it's going to take longer for it to fill up. So if I draw a quick graph, let's still call that time. We're going to call this the height. So if you think about, let's just write, maybe we'll put AB. No, wait, I'll leave that for a sec. So between here and here, it's going to take ages for it to fill up. So if it's going to take ages for it to fill up, then it's probably going to be a lower gradient, so the height's not going to go up very fast. I hope that kind of makes sense. So you could argue that there's a bit of a curve here, so it actually takes a shorter time for it to fill up towards a longer time. So a shorter time towards a longer time, so you might suggest that it curves. I can see that argument. So it's shorter and then it's longer. Let's call this, let's put A like around here, so then A might be here, this would be B taking ages. Now C, from B to C, it should be quicker to fill up. So it should be quicker to fill up. So I'm going to draw a line that's like quicker, actually not too quick, quicker, so that there's between B and C, and then from C to D it should be constant. So constant meaning a straight line, but the height is getting higher, and it should be heaps quicker, so like this. But again, this is just a very informal graph, it doesn't need to be amazing. I hope that made some kind of sense. One more, multiple choice. A bowl of hot soup sits on the kitchen bench cooling. At first it loses heat quickly, but as time passes it loses heat more slowly until it's room temperature. If you're going to do extension 1, this is stuff we're going to be looking at. Damn it, Krish, how did you get in here? Okay, So I guess we just need to think about which graph it's going to be. Now, this first one suggests that the temperature goes down and then it's just sitting there and all of a sudden it gets hotter. That doesn't really make any sense. This one suggests that it cools really fast and then it slows down. That seems realistic. This one suggests that it cools down slowly, then cools down really fast, and then just like becomes freezing. This one suggests that it cools down slowly, then fast, and then it plateaus. So I guess there's an argument for either B or C, but I'm pretty sure you'll find that if you're drinking a cup of coffee or something, it'll start cooling down very, very fast, and then it'll just kind of plateau. So the argument is the best one for B. And that's it. So that's a 20-minute video. That was kind of long. Apologize for that. But yeah.